So what we've been doing up till now is figuring out the slope of tangent lines, and that's basically what calculus is about and derivatives are about, is finding out the slopes of tangent lines. So now we have our definition of a derivative is sometimes called Newton's quotient. And we use this notation as one notation. We'll look at another notation as well. There's sort of two main people that came up with calculus, Newton in England, and this is his notation, and Leibniz in Germany, and he has his notation. And for the longest time, depending where textbooks came out of, you only saw either Newton or Leibniz, but not the other one, because there was an argument about who invented calculus and whatnot. So this is Newton's quotient. It's using his notation there. We say f prime of a. And all it is the limit as h goes to 0. We saw this already as one of the ways to find the slope of a tangent line. And that's all a derivative is. So f prime of a is the limit as h goes to 0. And again, the definition of a limit is something that you can get super close to. And all the derivative is the slope of that tangent line, the instantaneous rate of change. And that's what makes it so powerful, is you can find out how much something is changing at a specific moment in time on a point on a function. And here is the other form, right? And we saw this form as well. We will tend to use more the form as h goes to 0. And what we'll be looking at, if I go back to it, we'll be looking at, instead of looking at a specific point A, we'll be looking at what are the equation for all points A. So instead of saying at a specific point A, we'll just take any point x on our function. It will still equal the limit as h goes to 0. And now we'll have f of x plus h minus f of x over h. And this is what we're really going to use over and over again. As you can see, if we would do x instead of a here, this formula becomes a little bit confusing. Because if I put f prime x here now, x goes to x seems a little bit confusing. And then on the bottom you have x minus x, which is 0 right away, which is problematic. So that's why the other formula is the best one when trying to find derivatives. Here are a bunch of notations. F prime of x. Sometimes they just use y instead of f of x. Then you would just say y prime. Sometimes you don't have the x and you just say f prime. And then dy by dx, Leibniz notation. And we generally use this if we started off with y equals. Yes?
I've also seen it once where they put a dot over the y.
A dot over the y like this? I haven't seen that, but there's. Because often, you sure it wasn't just someone not doing a dash in the right spot? Oh, that's for the second derivative. Interesting. I haven't seen the dot, but I'm looking for new notations all the time. For a long time, like as far as notation going, why is there a bunch of notations for a bunch of different things? Well, mathematics was developed over different areas, and then different people had different symbols for different things. So you can look into the history of math. When did they decide to use the Greek letter pi for 3.14? Why do they use the letter E for 2.71828? And things like that. And there's history for all of those things and different people choosing different letters all the way through. Anyways, how are we going to find the derivative, f prime of x? Well, we're going to use the definition, and we're going to use that first one as h goes to 0. Okay? We're going to plug that, the function, whatever function we're doing, into the definition. Expand and simplify like terms if needed. Often we'll have to factor out h or use those skills that we had for evaluating limits so that an h will cancel out with the h on the bottom so we can actually evaluate our limit. So once we're no longer dividing by 0, in other words, no longer dividing by h, then you'll be able to plug in 0 and figure out what the derivative is. So, and we got the note about the conjugate and the strategies that we've seen before. Yes?
And when there is no way to simplify it, that the 0 will get out of the bottom since that limit doesn't exist.
Well, it just might mean that we don't have the skills to do it.
But then there is totally no way to do it.
Doesn't necessarily, the limit doesn't exist. So they keep, what you'll do in university once you study beyond the calculus you're doing here is you learn more techniques. Like what are techniques that if it didn't work with our normal techniques, what are new techniques that we could use to solve this? And now with technology, they can say, we can see from the graph that the limit exists. How do we prove that algebraically? Okay, so here is our very first example. Okay, f of x equals x squared. We need to find the derivative of this. Very powerful thing that we're going to do. We're going to use the definition. All I have here is two different notations. You wouldn't need to write them both. I just wrote them both just to show. It could be either one of those notations. If the question is asking for f prime of x, then generally you wouldn't have this, because it's just asking for f prime of x. And since the original equation used f of x, that tends to tell us we should use that notation as well. But again, there's not a deduction if you flip-flop between two notations that are the same. But if the question asks for f prime of x that way, it's sort of proper to respond in that way. Just like if someone asks you a question in English, even though you might speak Portuguese, you'll probably answer them in English, because that would be the proper way. Even though your answer may be correct in Portuguese, you would probably answer them in English. Okay, so f prime of x. So step one, we are going to plug in our function. So I'm going to write an equal sign here. I'm not going to rewrite f prime of x each time. I do have to write the limit as h goes to 0 each time until I evaluate the limit. And now what I'm going to do is I'm going to plug in. I have an x plus h inside of my function. My function squares things. So I'll have x plus h squared. Then I'll minus an f of x is x squared all over h. Next, we use our algebra skills until we can get things to factor out. So again, I have to write the limit as h goes to 0. This will be x squared plus 2xh plus h squared minus x squared all over h. And you probably can see our like terms that cancel out nicely. Yes? Nope. That is another way. So the idea here on the top, in this case, it's a difference of squares. If you would factor that, I'll do it in blue off to the side. I'll keep it over h. You would have x plus h, x plus h. One would be plus h, one would be minus h. Oh, sorry, plus x and minus x. Plus x and minus x. Okay? If you did that, what you're going to get once you simplify it is exactly the same thing I'm going to get in this line here. Okay? X goes, or h goes to 0. Can you see that once I cancel out my x squareds, I have something, and there's an h in common in both of those terms, which allows me to factor it out, h. I'd be left with 2x plus h inside the brackets. If you look at the difference of squares, I know I wrote it really beautifully here. This set of brackets will be 2x plus h. This set of brackets would just be the h. So factoring it as a difference of squares gives us the same factored form as we have if we expanded it and combined like terms. Here our h's cancel out. And now we're no longer dividing by 0. So now you can evaluate the limit and plug in 0 for h, and you will get just 2x. So we have f prime of x equal to 2x. So here is x squared, that's our black graph function, f of x. And what I have on here is I can take this point and drag it anywhere, okay? And it changes as I go along. Now, what I've designed this program to do is as I drag it along there, that blue line that's being drawn is the actual slope of my tangent as it moves along. Should I clear that so that we can start over again? Clear, clear, clear. Man. Oh, I'm getting rusty on this program. Undo. Yeah. There's a clear button somewhere too, but I'll just hit undo. Now, right now, the way that it started off is I've got my dot right there. It happens to be at negative 0.1 comma 0.17. And you see that I have a tangent line touching a curve at that point. That tangent line slope is negative, some value. And they've got the dot right there. They're saying that the slope is a little bit less than negative 1. Now what we found with our equation here, in the end, once we figured the whole thing out, is our derivative equation is 2x. What that means is if you would have picked a value for x, what we did before when we figured out what's the slope at the point, say, 3 comma 9. What's the slope at the point 3 comma 9? You would do this whole thing similar, but instead of x, you would write 3. And we did that right at the beginning. Now, since we did it with x all the way through, well, we could plug in 3 here at the end, and the slope should be 6. Now we go back to our graph here. If I drag this point, I'm going to have to zoom out a little bit here so you can see 3 comma 9. If I drag this point all the way until I get to 3 comma 9 right there, okay, it's telling me that the equation of the tangent is 6x minus 9. And we can see that the slope would be 6. We also know that on our derivative equation that when I plug in 3 for x, my slope is 6. So I plot the point 3 comma 6. And if I drag my point, there's my point, but actually drag the point, back and forth over and over again as far as I can, I hope you can see that it makes a line. That blue line that we just drew was this equation, y equals 2x, which we came up with. So there's a graphical idea of what's happening. When you put in x for your function, what you're going to come up with is an equation that finds every single slope all at once. And anytime you have x squared, the equation for all the slopes will be 2x. So if you wanted to find the slope at negative 4 on the original graph, you just plug in negative 4 for x, it's going to be negative 8. And we're going to learn shortcuts so we don't have to do this derivative thing every single time, which will also be really nice. That's the start of the next unit.